All right, guys, so clearly I am not at school, so you will be getting the notes via video. Today is the second day of optimization 3.7. We'll go through these two examples and then you guys can start working on the homework in class. Okay, so the first example, a person in a rowboat 2 miles from the nearest point on a straight shoreline wishes to reach a house 6 miles farther down the shore. If the person can row at a rate of 3 miles per hour and walk at a rate of 5 miles per hour, find the least amount of time required to reach the house. So I see least amount of time. So that means we're going to want to function in terms of time. Okay, and seeing the word least indicates we're going to want to take the derivative, all right, and look for a minimum. Okay. So I kind of worked ahead here and drew the diagram, so I'll kind of just point out everything. All right, so here is our shoreline, okay, and we have a person, P, that is 2 miles straight from the shoreline, okay. The house is 6 miles down the shoreline, okay. If the person can row at a rate of 3 miles per hour, so that's this guy here, all right, in the water rowing, and walk at a rate of 5 miles per hour, so once they get on shore, they're walking at 5 miles per hour. Okay, so that's kind of where we got the diagram from. So what we need to be thinking to get a function in terms of time is we need to initially think distance equals rate times time. And so how do we solve for time? Well, that just indicates time is equal to distance divided by rate. Okay, so I'm going to zoom in here a little bit and we'll get our equation in terms of time. Okay, so we kind of have two pieces. We need to talk about the distance over the rate for when they are rowing. Okay, and then we'll need to add the distance divided by rate of when they are walking. Okay, so our equation t of x is going to equal, well, how do we find the distance of the hypotenuse of a right triangle, right? It's just the Pythagorean theorem, or we can just take the square root of the sum of the squares of the legs. Okay, so it's going to be the square root of x squared, that red portion, okay, plus 2 squared, which is the distance from the shoreline, okay, over the rate of the rower is 3. Okay, but now we have to add this to the time for walking. Okay, so the distance that the person is going to be walking is going to be, well, it's 6 miles total, but we have to take away this x portion because they're not on land then. Okay, so the distance that the person is walking is simply 6 miles minus x all over, and the rate that they're walking is 5. Okay, so if we kind of clean this up to make it look a little nicer so that we can find the derivative, it's going to be the following. So we'll have t of x is equal to, and we can rewrite this as 1/3 times x squared plus 4 to the 1/2. Okay, plus, and I'll break up this other guy, 6/5 minus 1/5 x. So I did that just so we can find the derivative a lot easier. Okay, so there is our function in terms of time. So now we have to find the derivative. Okay, and we need to find our critical numbers so we can use the first derivative test and go from there. All right, so I'm going to shift down a little bit. Okay, so let's go ahead and find the derivative. So t prime is going to be, well, if I take 1/3 and I multiply by 1/2, I'm going to get 1/6 times x squared plus 4, now to the negative 1/2, and that chain rule, now we have to multiply it by 2x. The derivative of 6/5 goes to 0, and so then the derivative of that piece is just minus 1/5. Okay, so if we clean all of this up, the derivative is going to be x over 3 times x squared plus 4 to the 1/2 minus 1/5. Okay, so we want to set this equal to 0 so that we can find our critical numbers, right? So what we're really solving for is the following. We're going to have, well, adding 1/5 over to the other side and then kind of cleaning things up, we're going to get 5x is going to be equal to 3 times the quantity x squared plus 4 to the 1/2. So I skipped a couple steps in between. Hopefully you can follow. All right, so if I square both sides to get rid of that 1/2 power, we will get 25x squared. Don't forget to square that 3 out in front. So that's going to be 9, and then I'll distribute it right away, x squared plus 36. Okay, so we should be able to solve this hopefully relatively easily. So we get 16x squared minus 36 equals 0. And what will happen is, hang on one second, we will go ahead, well, we can factor that nicely if you wanted to, or you could go ahead and solve it. 4x plus 6, right? 4x minus 6. We could have simplified it earlier. And we'll end up with x is equal to plus or minus 3/2. So these are our critical numbers. T prime will not be undefined anywhere, so we just have to worry about when we set it equal to 0 this time. So there are some critical numbers, and now we just need to use the first derivative test and see where the minimum occurs. So we'll go ahead and shift over a little bit. Okay. So first derivative test. We'll test our points. We're going to be bounded between 0 and 6 because the house is 6 miles away from the point on the shoreline directly below the rower. All right, so really we don't have to worry about negative 3/2. We just need to focus on the positive 3/2. Okay, so T prime is what? Well, between 0 and 3/2, you should find that it's negative. And between 3/2 and 6, we should find it's positive. So what does that mean is happening to T? Well, that means we're decreasing between 0 and 3/2, and we're increasing between 3/2 and 6, which means this is where our minimum occurs. Okay, so this is where we can get our calculator out, and now we know our minimum occurs when T equals 3/2. So all we have to do is plug into our calculator T of 3/2. And when you do that, we should get 1.733, and then our units are hours. Okay? Okay, so there's everything kind of in a nutshell for you. So the least amount of time required to reach the house, 1.733 hours. All right, this next example, I already drew the picture ahead of time just to save some time. Take a look at it, all right? We want to find the maximum volume of a right circular cylinder that can be inscribed in a cone of altitude 12 centimeters and base radius 4 centimeters. If the axes of the cylinder and cone coincide, meaning that altitude area there, okay? So if we were to draw the diagram, it looks something like this, where the altitude this guy here of the cone, all right, is 12, and the radius of the cone is 4, okay, which is this piece here. And we are told we want to maximize volume, okay? So of the right circular cone. So we are maximizing volume. So we want an equation in terms of volume, and we'll have to find the derivative, and this time we're looking for a relative maximum, okay, with the critical points. So let's go ahead and remind ourselves what the formula for a cone is. Oops. Okay, so the volume of a cone is, if you can remember, pi r squared h. Okay, however, what we should notice is we've got two variables here, r and h. We only want one. So we're going to have to use this guy to set up some similar triangles, okay, to come up with what r is, okay, what h is in terms of r, I should say. So we'll set up a little proportion over on the side, okay. So if we have 12, that's the altitude of our cone, comparing to the radius of our cone, then we're going to set that equal to the height of our cylinder, which we don't quite know. We'll call that h, over that radius we're not so sure about. So we know that it's got to be 4 minus whatever that radius is, that distance there, okay? So if we cross multiply and we solve here for h in terms of r, we will get, 48 minus 12r equals 4h. Okay, so then we get h to be, 12 minus 3r. Okay, so we can make that substitution in now and have our equation of the volume in terms of our radius. Okay, so we've got pi r squared times 12 minus 3r. All right, and now we just clean this up. So the cleaned up version is going to be 12 pi r squared minus 3 pi r cubed. Okay, so that gets us our volume in terms of our radius. Okay, and again, we want to maximize this volume, so we now will find our derivative. All right, so if we find our derivative, we've got v prime is going to equal 24 pi r minus 9 pi r squared. So we can factor out a 3 pi r, and we'll be left with 8 minus 3r. Okay, so our critical numbers, we get r to be 0 and r to be 8/3. Okay. All right, so now all we have to do is use our first derivative test and see where our maximum occurs. So we've got 0, we've got 8/3. All right, so we'll see what's happening to v prime. So v prime less than 0, you should find that it's negative. V prime between 0 and 8/3 is going to be positive, and then we'll be back to negative everything after 8/3. So what does that mean? It means v is going to be decreasing and then increasing and then back to decreasing, and all we're looking for is where that maximum is going to occur. So there's where our maximum occurs. Okay, so now all we have to do to figure out the maximum volume is find v of 8/3 okay? And if we do, cleaning all of this up, we should get 256 pi over 9 when all is said and done, which is approximately 89.4 centimeters cubed. Okay, so the key here is obviously setting up the diagram, understanding what your function needs to be in terms of. Here we're maximizing volume, so we want an equation in terms of volume. Okay, tomorrow is our quiz. It is non-calculator. It is strictly on graphing, not this optimization. Okay, so when you get to class tomorrow, we're going to get right to the quiz. All right, if you do have questions, come see me in the morning. I'll be in the classroom. All right, have a good one. Thanks, guys.